So today we're going to be talking about the MOSFET differential pair. And we'll take a similar approach as to what we did in class on Monday. Today's Wednesday, right? Sounds right. In as much as we'll kind of look at how we think the amplifier should behave, and then circle back around to taking care of the math to make sure that that is actually the way that it works. So our MOSFET differential pair circuit is going to be effectively identical to our BJT differential pair, except that we're going to replace our BJTs with MOSFETs. So here we have some resistance RD. Here's our output voltage Vout1. We have some transistor M1, and we're going to apply a voltage VN1 to the gate of that MOSFET. Now on the other side of the circuit, I'm just going to effectively match that. Here's RD, Vout2, transistor M2, input voltage VN2, and now we're going to have a tail current ISS. And just to label a couple of things here, this current will be ID1, this current will be ID2, this voltage will be VGS1, and this voltage will be VGS2. Okay. So what happens when a common mode signal is applied to the inputs? All right, so effectively we have a differential input voltage VID of 0, which means that VGS1 and VGS2 are the same. And from that, quite obviously, ID1 must be equal to ID2, and this will be half of our tail current ISS. So if we look at our output voltages here, let's look at some things really quickly. So Vout1 should just be VDD minus ID1 times RD, or VDD minus RD times ISS over 2. And Vout2 would be VDD minus ID2 RD, which would also be VDD minus RD times ISS over 2. And our output voltage would be 0, which should make sense. There shouldn't be any difference in our between those two output voltage nodes if both transistor M1 and transistor M2 are carrying a literally identical amount of DC currents. So in a MOSFET, we don't have the luxury of being able to push our device into soft saturation and have it not really have any impact. So we're going to pay a little bit more attention today on the restraint of keeping our device effectively in its active mode of operation, okay? So since each transistor is carrying a current of ISS over 2, each transistor has to be experiencing an identical overdrive voltage, okay, right? Where our overdrive voltage is the quantity VGS minus VTH. So we could say that our equilibrium overdrive voltage, so VGS minus VTH at equilibrium, is going to come out to be the square root of ISS over mu n Cox W over L, where we are assuming that our channel length modulation coefficient is 0, which for the large signal is a relatively okay thing to assume. Okay. So this is going to pop up again effectively as a constraint that we are going to see later on, okay? So in order for us to ensure that M1 and M2 operate in saturation, so let me write that down. There is a constraint on the size of the voltage that we are allowed to apply as a common mode signal. So our common mode signal VCM will need to be less than or equal to VDD minus half RD times ISS plus a threshold voltage. Any common mode voltage higher than this is actually going to drive both of our capacitors into the triode region, okay? So there's a constraint as to the upper limit of what our common mode input signal can be. There's not really any constraint on the lower limit of our common mode signal as we are looking at this circuit right now. And what I mean by that specifically is if we put an ideal current source as our tail current, it doesn't care if the voltage drop across that ideal current source winds up being negative in order to keep those things in saturation. When we replace that tail current source with a transistor current source, then there will be a lower limit as to what our common mode signal can be as well. But for now, we just have an upper constraint to keep us in saturation. All right, so now let's talk about what happens when VN1 is greater than VN2. So when VN1 is greater than VN2, that means our differential input voltage is a positive quantity, which in turn means that the voltage VGS1 will be greater than VGS2, and thus transistor M1 carries more current. Than M2. If VGS1 is much greater than VGS2, M2 will turn off or enter effectively cutoff mode, making ID1 equal to ISS and ID2 equal to 0. So under this constraint, where VGS1 is much greater than VGS2, we would find that our output voltage 1 is VDD minus RD ISS. Our output voltage 2 would just be VDD, and V out in this case, which is just V out 1 minus V out 2, is negative RD ISS. So we once again get a negative output voltage when the current on the left-hand side is greater than the current on the right side. And then without writing all of this stuff down, what would happen if VN2 were greater than VN1? The exact opposite, all the way to the point where our output voltage would change in polarity. So if I were to graphically represent what's going on here, we'd see something like this, okay? So I'm going to have two graphs that are going to be very, very similar. So this axis is going to be our differential voltage, and then the vertical axis is going to be for our currents. And what we're going to wind up getting is something like this. Actually, let me put some dashes here. So this is going to be our midpoint. So when VID is equal to 0, we know that both of our currents are supposed to be half ISS. So we would see that ID2 would do something like this. ID1 would do the exact opposite. And this topmost value up here corresponds to a current of ISS. So all I'm trying to illustrate here is effectively that this device also provides current steering. So whichever side we apply our input voltage on drives more current to that side. If we were to look at our output voltages as a function of differential input voltage, we'd have a similar looking graph. So this corresponds to VID is 0. This right here is going to correspond to VDD minus 1/2 RD ISS. We look at V out 1. Let me change the color of that to blue since it's for the one side of things. Sorry about that. V out 2 would do something like this. And up here we have VDD, and down here we have VDD minus RD ISS. All right, so this is roughly what things are going to look like. Now we're going to figure out the supporting math that goes behind why things behave this way. And like I said at the end of our last class meeting, this math can get a little bit gross because of the current voltage relationship for our MOSFET transistors. Okay. So for our qualitative analysis, we're going to be looking at effectively the same circuit that we were looking at just a moment ago. And we're going to do the exact same process where we apply half of our differential input voltage on one side and half on the other side. So here's V out 1. Here's transistor M1. Our input voltage VID over 2. Here's M2. Our input voltage negative half VID over 2. Excuse me. And our tail current ISS. Just identifying my currents and voltages really quickly here. ID1, ID2, VGS1, and VGS2. And much like we did on Monday, our goal is to figure out what our differential output voltage is as a function of our differential input voltage. And we're also going to wind up figuring out what the change in our drain current is as a function of our differential input voltage. Our drain current for our MOSFETs, 1/2 mu n Cox W over L times VGS minus VTH squared. If we call this thing right here K sub n, and we rearranged, and I think I showed you guys this relationship recently, we could rearrange this to find that VGS could be written as VTH plus the square root of our drain current over Kn. Yes. So these are large signal differential volts. So we're not looking at the small signal anything. Everything we're doing here is large signal. Good question. All right, so let's start by looking at our output voltage, much like we did for our BJT device, right? So V out 1 is just going to be VDD minus RD ID1. V out 2 is going to be VDD minus RD ID2. And from this, our differential output voltage VOD is just the difference between V out 1 and V out 2. And that's going to look like negative RD times ID1 minus ID2, or negative RD times delta ID. So the difference in our drain currents. Okay. So now we can see where and why we need to figure out the relationship between delta ID and VID, because we've got something easy to plug things into. So to start that, we're going to do something extremely similar to what we did on Monday. We're going to write that same KVL equation. So starting from ground down here, we're going to go cross this path, and that's going to give us VID over 2 plus VGS1 minus VGS2 minus VID over 2 is equal to 0. And from that, we can see that VID, our differential input voltage, is just the difference between VGS1 and VGS2. And taking this one step further, we can use this expression to relate those VGSs to our drain current, right? So we're going to have VTH1 plus the square root of ID1 over KN1 minus VTH2 minus the square root of ID2 over KN2. Yes. Mm-hmm.
How do you get there?
Oh, actually, I'm sorry. That should be an equal sign. My apologies. If I needed a negative sign on the front of that thing. Thank you for that catch, Ryder. You were 100% correct that there was a mistake there. All right, so let's make an assumption here. And our assumption is that both of our transistors are matched, right? So if we want this thing to act as a good differential amplifier, we need transistor M1 and transistor M2 to be identical to each other. So if M1 and M2 are matched, VTH1 is equal to VTH2, and KN1 is equal to KN2, and so we're just going to call that KN. So if VTH1 and VTH2 are equal to each other, the threshold voltage portion of our differential input voltage goes away. We're just left with square root of ID1 over KN1 or KN minus the square root of ID2 over KN. I'm going to factor out that 1 over K. And so we're going to have VD is equal to 1 over the square root of Kn times the square root of ID1 minus the square root of ID2. Now we're going to do a little bit of manipulation for this guy, okay? So I'm going to do this in a separate color so I can show you what we're doing over here. So we know that ISS is ID1 plus ID2. And we know that delta ID is ID1 minus ID2. And using those relationships, we can actually write our differential input voltage as 1 over the square root of 2 Kn. So I'm going to wind up with a factor of 1/2, and I'm just going ahead and moving it outside from this manipulation. And then I'm going to have the square root of ISS plus delta ID minus the square root of ISS minus delta ID. Now, I know that looks odd, but if we add ISS plus delta ID together, we just get twice ID1. Take out a factor of 2, and this bit right here literally just represents half of ID1. Or this guy right here, twice ID1, we take away 2. When we subtract those guys, we are going to get twice ID2, take out that factor of a half, and so that's where our substitution comes from. So I understand that it looks odd, but it all shakes out to be pretty okay. So our goal here is to figure out what delta ID is as a function of the ID. And so in order to make that happen, we've got to get rid of these square root signs, which means we're going to be squaring some things, okay? So I'm going to move the square root of 2kn over to the differential input voltage side of things and then square both sides. And so that's going to wind up giving me twice kn VID squared is equal to ISS plus delta ID plus ISS minus delta ID minus twice the square root of ISS squared minus delta ID squared. Are we okay with that? So the delta IVs wind up canceling each other out. We've got a common factor of 2 on both sides. So let me write this thing out like this. So this ID right here cancels out this minus delta ID right here. We've got ISS plus ISS. That's going to look like twice ISS. We have a factor of 2 on that square root term. We have a factor of 2 on the left-hand side of our equation. So all of those 2's go away. And so this reduces to Kn times VID squared is equal to twice ISS minus, actually, sorry, that twice should go away. My apologies. Square root of ISS squared minus delta ID squared. And moving on from here, we could say that the square root of ISS squared minus delta ID squared is going to be equal to ISS minus Kn VID squared. Square both sides yet again to get rid of this extra square root sign. Gives us ISS squared minus delta ID squared is equal to ISS squared plus Kn squared VID to the 4th power minus twice Kn ISS VID squared. We have an ISS on both sides of the equal sign here, so we can get rid of those guys. Moving our negative sign over, we wind up finding that delta ID is equal to the square root of twice Kn ISS VID squared minus Kn squared. VID to the fourth power. And then I can pull out a factor of Kn times VID from my square root sign, leaving me with Kn times VID times the square root of twice ISS over Kn minus VID squared. Replacing, let me go back here to see exactly what I called. Okay. So here I called Kn 1/2 mu n C ox W over L. So I'm going to back substitute that back in here. And so that's going to wind up giving me 1/2 mu n C ox W over L times our differential input voltage times the square root of 4 ISS over mu n C ox W over L minus VID squared. And I wanted it specifically in this form so that we could look at something here. Okay. So what's happening when our differential input voltage VID squared gets to be the same thing as 4 ISS over mu n C ox W over L? That bit under the square root sign is going to go to 0, which means our differential current is going to go to 0. Does that make sense? So let me write this out. So based on this equation, it appears that delta ID approaches 0 as VID squared approaches 4 ISS over UN C ox W over L, right? So when this guy right here is equal to this guy right here, our current goes to 0. And I asked the question, is that okay? So does it make sense that the difference in our currents trends towards 0 as we let VID get large, either positive or negative? No, it should approach ISS, right? So if I were to plot this expression, what it would look like is something like this. So here's delta ID. And I'm going to try to make this as symmetrical as possible. So bear with me. Actually, that's too far already. something like that. As a function of VID. This is not our expected behavior. What we were expecting was something more along the lines of this. So effectively, it's this guy right here that's wonky, and this guy right here that's wonky. So beyond some certain threshold, to figure out what that is in a minute, our model fell apart. What do you think the issue is? So we mentioned it earlier when we were looking at things qualitatively. When one of the transistors starts carrying effectively all of the current, the other transistor turns off. All of our math here has assumed that both transistors are constantly in saturation, which can't be true if one of them turns off, right? So there's a limitation, okay? So at the point where one of our transistors is operating effectively at the edge of conduction, so let's say when M1 carries all of the tail current, VGS1 will be VTH plus twice excuse me, that should be ISS, not IDD, that's not a thing, over mu n Cox W over L, and VGS2 could effectively be VTA, meaning that it's on the edge of turning off at any given moment, right? So this relationship effectively tells us what our differential maximum input voltage is going to be. So our maximum value for VID is going to be square root of 2 ISS over mu n Cox W over L, which is the difference of those two things. And if we look back up here, look too far. That's literally just the square root of 2 times our equilibrium overdrive voltage. So from this, we can say that our differential output voltage, VOD, is negative RD times delta ID, which will, doing simple substitution here, give us negative 1/2 mu n Cox W over L, VID RD square root of 4 ISS over mu n Cox W over L minus VID squared. where the absolute value of VID max is root 2 VBS minus VTH. Sorry, I'm running out of room here. Equilibrium. And graphically, we're going to have something like this. So this is VOD on this axis, VID on this axis. And we have a constraint that here is negative VID max. And over here is positive VID max. So there is a specific limit on the size of not only the common mode signal that can be applied, but also the differential mode signal that can be applied. What happens if we exceed our differential mode signal constraint? Anybody care to venture a guess? So it's just going to tie the output to DC effectively. All right, so this is our large signal analysis of the MOSFET differential pair. It's all I wanted to talk about for today. So when we get back from the Easter holiday, which I hope you guys have a safe and good, effectively week-long break from my bullshit, we're going to tackle small signal analysis, which will be much, much easier than all of this stuff. All right, you guys have a good holiday.